Now we are going to deal with a slightly different type of compound inequality. In this case, we're going to deal with the exact same individual inequalities, but we're going to replace the word and with the word or. So consider the compound inequality 4d minus 7 is less than 8 plus d, or negative 5d plus 7 is less than or equal to negative 3. And our initial strategy is going to be exactly the same. Let's solve each of these individual inequalities and then graph their solution sets on the same number line. So why don't you pause the video and you take care of that, and when you're done, please play the video and we'll reconvene. Now, to be a solution to a compound inequality involving or, the number doesn't have to make all of the statements true. The number, when substituted in for its variable, must make at least one statement true. That is, the number must be a solution to any one of the individual inequalities in order to be a solution to the compound inequalities. So, let's take a look at the number line. Again, any number in red is a solution to negative 5d plus 7 is less than or equal to negative 3. Any number in blue is a solution to 4d minus 7 is less than 8 plus d. So if a number has been colored at least once, if a number has been colored at all, then that number is a solution to this or compound inequality. Well, when I look at this number line, I think that every single real number has been colored at least once. So in this case, we would say that all real numbers are solutions to this compound inequality. Whatever number you pick, when we substitute it into these equations, it will make at least one, if not both of them, true. Now, we have the choice. You can shade the entire real number line if you'd like, but since the solution set is all real numbers, this is the one time that you don't actually have to shade it all, because the reader knows all real numbers are solutions. Here's another compound inequality that we've seen before, this time with an or in between the two individual inequalities. Again, I'd like you to pause the video, please solve each of the individual inequalities and graph them on the same number line, then play the video and we'll reconvene. So, after solving each individual inequality and graphing it on the number line, we see that there are some numbers that are not colored in at all. And those numbers don't make either statement true, so they are not solutions to our or compound inequality. However, there are lots of numbers that are colored in once or twice. All of these numbers are solutions to at least one of the individual inequalities, so they are solutions to our compound inequality. If we wanted to shade in our solution set, here's what it would look like. And if we wanted to write our solution set algebraically, we would just say w is greater than or equal to negative 4. Another familiar compound inequality from before, of course this one now separated by the word or instead of and. So again, if you pause the video now, please solve each of these individual inequalities and graph their solution sets on the number line below, and when you're done, please play the video and we'll reconvene. This time, after solving each individual inequality and graphing them on the number line, we see there are a few numbers in the middle that aren't colored at all. Those numbers satisfy neither of the inequalities, so they are not solutions to our or compound inequality. But there are two different regions of numbers that do make exactly one of the statements true. They're not conjoined, so there's no quick and easy way to write down the solution set for this compound inequality. We'd actually say in this case, the solution set is g is less than or equal to 3, or g is greater than 7. It's a bit awkward, but there's no easier way to write it in this case. Here, we've got all the possibilities for what the outcome could be with an or compound inequality. So, like before, I'd like you to pause the video, and I'd like you to write and graph the solution set for each of these 6 possibilities, recalling that in order to be a solution to an or compound inequality, you must be a solution to any of the individual inequalities, or at least one of them. In each of these examples, remember, as long as you are shaded at least once, or shaded at all for that matter, you are a solution to that OR compound inequality. And so you see for you graphed and written algebraically the solution sets for these 6 possibilities. Alright guys, that's it for this video. I hope you enjoyed, and I hope you found it helpful.